This is another nice paper. Such review papers are important and they are written by community, lots of authors. This one is led by Antoinetta Capatondi, who I think is still at uh, NCAR in Boulder, if I'm not mistaken. But anyway, she put together a team and they put together this nice review article on the mechanisms of tropical Pacific decadal variability. Usually, when you say mechanisms, are there many mechanisms, or is it that they are potential mechanisms? Obviously, we don't always have a complete understanding of these things, and there are often many players involved because there are interactions between the modes. But what is specific decadal variability? Tropical Pacific decadal variability. Some of you may be aware of the Pacific decadal oscillation, which is an off tropical thing. It's focused on the mid latitudes, even though it has a very strong tropical signature, and they are not independent. Naturally occurring tropical Pacific variations at timescales of 77 to 70 years, tropical Pacific decadal variability or TPDV, describe basin scale sea surface temperature, sea level pressure, and heat content anomalies. We'll see a picture soon. Several mechanisms are proposed to explain TPDV, which can originate through oceanic processes, atmospheric processes, or as an El Nino Southern Oscillation residual. You have multiple El Ninos. There is some kind of a low frequency rectification signature is left behind that appears as decadal variability. If you remember, El Nino Southern Oscillation is an interannual variability. And if you don't know, you can follow up with the other podcasts on my channel. In this review, we synthesize knowledge of these mechanisms, their characteristics, and contribution to TPDV. Oceanic processes include off-equatorial Rossby waves, which mediate oceanic adjustment and contribute to variations in equatorial thermocline depth and SST, variations in the strength of the shallow upper ocean overturning circulation, which exhibit large anti-correlation with equatorial Pacific SST at interannual and decadal timescales, and the propagation of salinity compensated temperature anomalies, which we call spiciness, from the subtropics to the equatorial thermocline. Atmospheric processes include mid-latitude internal variability leading to tropical and subtropical wind anomalies, which result in equatorial SST anomalies and feedbacks that enhance persistence, so things can last, which makes it a low frequency mode like decadal variability, and atmospheric teleconnections from the Atlantic and Indian Ocean SST variability, which induce winds conducive to decadal anomalies of the opposite sign in the Pacific. Although uncertain, the tropical adjustment through Rossby wave activity is likely a dominant mechanism, so we are still kind of putting together the story. A deeper understanding of the origin and spectral characteristics of TPDV-related winds is a key priority. Again, the understanding is not complete. So let's look at, oops, I did something wrong here. Let me adjust it in near real time. And I have it here. Yeah, so I need to remove this. Which I can just cut out and then go back. Sorry about that. Mean ocean and atmospheric circulations in the tropical Pacific. We can just look at the picture and understand. So we have in the climatology, we have, do I have the pointer up yet? Yeah. We have strong trade winds which push the water to the west, which means Coriolis push it away from the equator. So you have upwelling, which means thermocline comes up in the east and the waters pile up and warm up on the other side. So it's deeper on this side. So you can see the equatorial divergence, convergence below the surface, and upwelling, which exists across here. So you have various types of arrows, but basically we are saying there is equatorial upwelling, east to west SST gradient, as well as a thermocline gradient in the opposite direction. So SSTs increase this way and thermocline shallows this way, right? So this is the equatorial undercurrent below, and you can see on this side this nice tropical subtropical cell that we say. And in the atmosphere, you have the manifestation in terms of the strong convection, the so-called boiler box on the maritime continent, Western Pacific, which produces about 5 meters or so of rain. That air diverges in the meridional direction, which we call the Hadley cell, but in the zonal direction becomes the Walker cell. We call this the Pacific Walker cell. You have north equatorial countercurrent, equatorial undercurrent, south equatorial current, and so on, which have vertical structure, horizontal structure, and of course, we are showing also the Hadley circulation here. So there is also the Indian Ocean side of the Walker cell and the Atlantic side of the Walker cell. So you are showing sea surface temperatures, subsurface temperatures, and zonal current speeds in meter per second. So you have all these nice circulations. I think if you haven't followed this up, to go and look up in my El Nino lectures, it's all in there. Also in the tropical dynamics course, we have that. We have, of course, the Indonesian through flow that's going through here from the West Pacific into the Eastern Indian Ocean, the ITF, and there is the Lewin current, there is the East Australia current, there is the Kuroshio here, and a California current on this side, or the Peruvian current on this side, and so on and so forth. So TPDV as an ENSO residual, this is a nice long paper. I'm going to again reduce it to a brief summary. You can go and read, and as usual, review article means lots of very nice references that you can follow up on. Since the tropical Pacific climate is dominated by interannual SST variations, a plausible hypothesis is that TPDV arises as a residual of ENSO. Indeed, the ENSO-like TPDV spatial pattern can also be reconstructed from decadal averages of evolving ENSO patterns from their developing or to decaying phases and from the random event-to-event variations of those patterns. In addition, uneven numbers of warm El Nino or cold La Nina events randomly occur during different decadal epochs, so which you'll see in a minute, resulting in El Nino-like or La Nina-like decadal conditions. The location of SSTA during these uneven events, whether anomalies are centered in the eastern or central Pacific, might also contribute to the low frequency background changes. Basically, there are nice papers which tells you how El Nino pattern is different. It's a bit more symmetric about the equator than the or El Nino pattern. La Nina pattern is more asymmetric than El Nino pattern, and when you superpose them, you end up with some low frequency rectification and some patterns. Okay, so what are the hypotheses in these things? There is a so-called V bar T prime hypothesis and wave processes. So in addition to the possibility of being an ENSO residual, equator advection of temperature anomalies T prime within the pycnocline, the V bar T prime hypothesis, which we'll look at later, has been put forward as a driver of the TPDV. Two mechanisms by which subtropical signals reach the equator have been proposed. The spiciness anomalies advected as passive tracer by the mean circulation, and non-compensated temperature anomalies propagating as planetary waves or Rossby waves. The details are given, which I'm going to skip because they are basically consistency checks on what can be diagnosed from models and observations, mostly from reanalysis data. And there are lots of issues about whether these spiciness anomalies or salinity compensated temperature anomalies basically means you're carrying some kind of a density anomalies, which somehow remain unmixed all the way from the subtropics to the tropics, and people disagree with it, agree with it. There are evidences for it and how they get across the ITCZ and so on into the tropics. And, there are pathways they have to follow and so on and so forth. Very interesting, but again, hypothesis, okay? Or you can just have waves, which obviously can move non-compensated temperature anomalies. So salinity is not compensating there in terms of density. And then there is the V bar T, V prime T bar hypothesis, where the mean temperature structure is being subjected to anomalous meridional advection. In addition to upwelling of anomalous temperatures from the pycnocline, anomalous upwelling can also drive TPDV via changes in the transport of the STCs themselves that we looked at here. So if they are pumping up or down, can you change the low frequency variability in the tropical Pacific, right? At decadal time scales. So specifically, an increase in equatorward mass transport of the STCs enhances equatorial upwelling, bringing colder pycnocline waters closer to the surface and cooling SSTs. Reduced STC transport has the opposite effect. And at interannual timescales, these changes encapsulate the recharge-discharge of the equatorial upper ocean heat content, which we discuss a lot during the ENSO evolution. So during normal years and La Nina years, the trade winds are pushing water to the west, upwelling is happening, waters on average are getting warmed, so the warm waters are collecting in the deep tropics across the entire tropical Pacific, and then when discharge happens, the warm waters slosh eastward, we get Bakeness feedback, and so happens, and then the recharge starts again, and we know that, right? At interannual timescales, this is what happens. The relationships at decadal timescales suggest that similar underlying dynamics might be important at lower frequencies. In other words, we are still speculating on exactly what's happening based on what we can infer. And then we look to see what the models are doing. And models are not perfect, but they do and so with a bias, sometimes too regular and so on. And sometimes they produce low frequency variability as well. And you basically have to look for dynamic consistency within the model. If it is doing MSOs and if it is doing TPDV, then what is the mechanism in the model and how does it correspond to these reanalysis products that where we blend models and data and so on. So these are the SST difference. So let's read the caption first. Observed Pacific decadal changes. The differences of linearly detrended sea surface temperature anomalies in the shading and decadal SST anomalies regressed onto the tropical TPDV index. B, the differences linearly detrended of linearly detrended sea level pressure, and we have that's temperature difference in the West Pacific and temperature difference in the East Pacific. So together you have SST differences. You can see the PDO structure with the Aleutian low, and there is also a North Pacific gyre mode. There is a Pacific meridional mode. All kinds of things are understood in similar frameworks with tropical wind response to off-tropical variability and so on. And of course, it has a hemispheric signature, interhemispheric signature as well. If you look at the sea level pressure difference, of course, you have again wind signatures in the tropics, and you have corresponding off equatorial signatures. The Southern Ocean makes it difficult. And now there is something called ENSO transition mode that has just been reported by Shikhar Srivastava and his advisor Arindam. I was involved in it, which argues that there is something going on in the southern Pacific which produces wind anomalies here, which also explains the decadal seasonal transition of ENSOs, how the ENSO transitions from the winter peak to the following summer. Will it go from warm to warm, warm to cold, cold to warm, normal, neutral, and so on? So these are the SSH differences which correspond to the warm SSTs because there is heat content buildup and depletion of heat content, but you can see the differences that the uh, SSH signature is more towards the subtropical gyres and the western boundary currents. And of course, these are not detrended. So these are hotspots of sea level rise and warming. So you can see some differences emerge that are kind of maybe amplifying the same thing. Okay, so some differences here, but mainly it's just deepening of these patterns and these patterns here. Okay, so the temperature differences in the West Pacific again show the tropical subtropical cell, and here it shows the tropical subtropical cell in the east with upwelling signature, and here deepening of the thermocline signature. So near the surface you have sea surface temperatures, but these are basically the isothermal movements or isopycnal movements and so on. If you think about relationships between tropical Pacific decadal variability and El Nino southern oscillation, You look at sea surface temperatures. So this is including interannual variability. There is SSH, which is in the West Pacific and in the East Pacific. And the TPDV index shows this which is basically defined. Let's see the evolution of the tropical Pacific decadal index computed as the leading principal component of decadal, so 7 to 70 year SST anomalies over 25 south, 25 north. More El Nino activity and prevailing negative heat index anomalies in the western tropical Pacific are associated with positive TPDV phases and vice versa. Of course, people argue whether we have long enough data to even capture 70-year cycles, because you need to have few cycles in the data before you can claim a 70-year variability. But nonetheless, we do this with whatever data we have. We are going here from 1960 to 20, uh, 2020, let's say, it doesn't matter. This is 10 years here, so about 7 or 8 years. But obviously, we are still inferring the TPDV index of 7 to 70 years, and it clearly has different time scales. Some are longer, some are shorter in terms of the positive and negatives in this. So subtropical cells influence on the tropical Pacific decadal variability is implied in the way we do these things. So you look at the subtropical cell influence on the tropical Pacific decadal variability with V bar T prime and V prime T bar mechanisms. So this is the way they are showing it schematically. Pacific Ocean V bar T prime hypothesis is basically saying here North America. So that's the uh, yeah, so we are looking, we have to be careful how we are looking at this. So here is the latitude. We are going from equator to 40 north. So they have reversed it. This is going south here. So you have Australia here, ice signal outcrops, which means basically what you are tracking has disappeared. And here is the depth. So you can see that over to the north. Uh, so just orient yourself, okay? So we are looking at here to here, okay? So just be sure where you are. And it's confusing, but you are basically trying to bring mid-latitude waters into the tropics. So you have the longitudes here going from eastern Pacific towards the western Pacific. So you have potential barrier, potential vorticity barrier, which is the ITCZ that I mentioned. So waters cannot simply cross them. So that's near the equator. So here is a low latitude western boundary current is bringing the mean currents are shown in these arrows, and then temperature anomalies are shown in this purplish color, and you are showing the background colors, background depths of the thermocline, right? So you go north, thermocline is deeper, you come towards the equator and the west, you have, this is low frequency. So essentially what we said before, that the mean meridional circulation or the subtropical cell is bringing non-compensated temperature. That's the hypothesis. It's a fancy diagram, but you can see it better here in the zonal average isopycnal. From the north and from the south, you have uh, waters in the subsurface coming towards the deep tropics and being upwelled. And all this is happening at low frequencies. So what exactly pumps up and down the thermocline and the STCs themselves? Obviously, that's related to whether it's being forced internally or within the tropics, or whether it's coming from outside, and all those kinds of things. Similarly, you have V prime T bar hypothesis. Again, you are looking at the potential vorticity barrier, so you have to get around it in the low latitude western boundary current, and then get into the equatorial undercurrent to come towards the east and upwell. So that's the east there. So this is the reds are the current anomalies. So you have the mean circulation, the current anomalies, and here you just have the mean currents, V bar, bringing the T prime. And here they look different. So you have STC, subtropical cell anomalies happening over the mean circulation that are bringing compensated or spiciness anomalies. And there are many details in terms of meridional pycnocline transport from the north across 9 north and across the south in the southern hemisphere. So this is the volume transport. So this is southward transport, northward transport towards the tropics, and this is over time. Sorry, this is, yeah, across 9 knots over time, right? So that tells you that there is decadal variability. Meridional transport convergence observed. These are very nice papers that are also there with Mike McFadden and Chris Mine and so on and so forth. So if you look at the meridional transport convergence from the reanalysis products, the correlation is 0.82, which says they're all doing similar and with SST. So there is a relation between circulation and SST, which is not surprising, but it still doesn't fully explain the mechanisms in terms of V bar, T prime, V prime, T bar, and so on, or waves versus advection. Meridional transport convergence, low pass filtered and SST low pass filtered correlation jumps up, but the degrees of independence go down, of course. Transport convergence, equatorial SST relationships, I won't go into the details, but you get the idea. Why am I being so brief? Because these are nice discussions and they discuss what we know, which is very important to know what has been proposed by different people, but also says that we don't have a complete answer yet. So response to the North Pacific meridional mode that I mentioned before, and response to the South Pacific meridional mode. So we have these meridional modes which were proposed for the North Pacific first by, I think, John Chiang, Dan Plymont, and so on. And now later on, we also ended up with the South Pacific. So this is the northern latitudes here. You can see the connection from off equatorial SST forcing to equatorial winds and feedbacks. And you have the same thing here happening in the South Pacific, and responses to decadal Indian Ocean SSTA. More and more studies are showing that Indian Ocean warming is affecting the Pacific, even in the trend sense that the heat uptake and the east-west response difference in the Pacific to anthropogenic forcing is also being modulated by the Indian Ocean, and the Indian Ocean is also argued to accelerate the Atlantic meridional overturning circulation and so on. And this one argues also responses to decadal Atlantic SSTA, which has also a pattern here that you can see. So does this mean this is sitting here and responding to these, or there is a feedback and the same thing here, and whether these are independent or they are the same thing, and whether this is the same as the ENSO transition mode, and so on and so forth. So you have observations that say that we have a tropical Pacific decadal variability. We have signatures that you can link the connections from the Indian and Atlantic Oceans into the Pacific, of tropical signatures into the Pacific. It can be mean meridional circulation bringing anomalous temperatures, or anomalous meridional circulation bringing mean temperatures, and so on and so forth. Everything is in play, waves, advection, spiciness, non-compensated, but we still have not the correct total answer. So paleo evidences 7 to 70-year bandpass filtered mean of 3.4 standard deviations. Instrumental observations for 1850 to 2015 show some energy there. CMIP6 historical models, so how many models are used and what time period is used. You can see the range is very different, but for 1990 to 2005, in CMIP5 historical runs, the previous version. You can also go back to CMIP5 and PMIP3, Paleo Model Intercomparison Project, which looked at 850 to 1850, so the last millennium, which has also the signature of decadal variability. And of course, corals show some signature field reconstructions and paleo data assimilation. Okay, so we are doing everything we can to understand these things. What is the summary and future perspectives? TPDV of 7 to 70 years is linked to coherent basin scale SST and SLP anomalies with global impacts. Despite a limited historical record of subsurface data, surface manifestations of TPDV are also associated with a reorganization of tropical Pacific upper ocean heat content, most notably in the zonal direction, suggesting the involvement of ocean dynamic processes. Indeed, several mechanisms have been proposed to explain TPDV. In generally, several mechanisms means we don't know the correct answer, or many hypotheses are in play. Although it is plausible it might simply arise as a residual of random ENSO variations, TPDV leads to decadal ENSO modulation by a few years. So El Niños cluster, more El Niños or more La Niñas, and then fewer, and so on. And TPDV leads. And so it raises a question of whether previous cycle of ENSOs is doing that, or change in TPDV, phase shift in TPDV is leading to ENSO clustering, right? So if you look here, do ENSOs cluster and cause the phases, or does the phase change cause clustering of ENSOs? So that's an interesting question, which is hard to answer. Okay, so this lead lag relationship suggests that ENSO decadal changes are likely a consequence of the slowly varying background conditions, not their cause. A strong relationship between decadal variations in the strength of the STCs and the equatorial SSTAs provides support for the V prime T bar hypothesis. However, the largest correlations occur at zero lag, making a causal relationship between STC transport and equatorial SST changes unlikely. Instead, concurrent STC and equatorial SST variations are part of the tropical peak-to-decline adjustment to varying wind forcing mediated by Rossby wave activity. Right? Thus, these wave-mediated adjustment processes encompassing the non-compensated component of the V bar T prime hypothesis emerges as a robust feature of TPDV. For instance, Rossby wave activity alters peak decline depth and manifests itself as temperature anomalies that propagate on mean isopycnals. Okay, somehow background structure is there, and then anomalies are riding on top because it's easier to ride along isopycnals energetically. Contributing to TBDV this way, given their transit time and interaction with the forcing, the latter including preferential response to the larger spatial and temporal scale of the winds. Propagation of salinity compensated temperature anomalies, spiciness anomalies in that sense, is also supported in modeling context as a potential mechanism. Yet, limited observational evidence of anomalies reaching the equatorial region, in addition to a small modeled influence, call into question the magnitude of the compensated V bar T prime component. Okay, if T prime has to survive all the way, even if compensated by salinity, just doesn't seem to reach across the potential vorticity barrier, let's say. The atmospheric response to decadal SSTAs in the equatorial Pacific, internal atmospheric variability in the context of extratropical Pacific and atmospheric influences from the Atlantic and Indian Oceans are all potentially important drivers of the aforementioned oceanic processes. Finally, a major limitation in our understanding of the TPDV stems from the relatively short observational record, which does not allow a robust characterization of decadal variability and a proper assessment of climate models' fidelity in simulating it. If we cannot nail it down in the observations, then uh, saying whether the models are right or wrong becomes very difficult. More extensive investigation of TPDV using multi-century paleoclimate records could provide critical insights on the key features of TPDV and better constrain models with better constrained model evaluation at decadal timescales, but typically paleo records are far apart, and they are not it's not always clear with what scale they represent, right? If you find coral data in the east or west or north somewhere, sediment data, whatever, how representative are they? That's really the question. This review has not addressed the question of how TPDV might change in response to external forcing, such as anthropogenic forcing. However, changes in the characteristics of TPDV as a result of anthropogenic forcing can be expected. Increasing sea surface temperatures will result in increased ocean stratification, leading to faster Rossby wave propagation, shorter adjustment timescales, and reduced growth and predictability of Pacific decadal variability, which might lead to weaker, shorter time scale TPDV in the future. So we don't know TPDV very well. We don't understand the models, whether they're doing it right or wrong, but we speculate about the future nonetheless. The expected reduced influence of the Atlantic variability on ENSO owing to increased tropospheric stability can also reduce the influence of the Atlantic decadal variability on TPDV. Yet, the wind evaporation SSD feedback is projected to increase owing to warmer sea surface temperatures and increased evaporative response, leading to an enhanced impact of the North Pacific meridional mode on ENSO and possibly on TPDV. These and the other possible processes and their interactions need to be assessed in climate models to determine how TPDV might change in a warmer world. Right? We didn't talk much about the impacts of TPDV here, but if you cluster El Niños and La Niñas, there will be plenty of impacts, even though right now we don't know whether uh, ENSOs are clustering TPDV, which seems likely, that or ENSO clustering itself is generating TPDV, in which case you have to explain what is causing ENSO clustering and so on and so forth. But obviously, it's the important mode of variability that is observed and seems to be there in the data, so we need to understand it and explain it. And these people will continue to work on it, so new results will keep coming, and I'll keep my eye on them and let you know if there is some new breakthrough on these. Okay, I'm being brief. Still, it's 30 minutes long, 31 minutes long, but the paper is nice and long, so you can go and read more details. Okay.